Hello, this is Mr. G, and it's time for another fun physics lesson. Okay, sorry I've been out of school. I've been a little under the weather, okay, as in kind of sick, but I should be getting better. So, anyway, physics goes on, okay? So, what we're going to do for this lesson is to talk about friction. Friction, okay? We've talked about this before. That is a force that opposes slipping between surfaces, right? A force that opposes slipping. It does not oppose motion. It makes motion possible, actually, and it makes stopping possible, okay? What it opposes is one surface slipping or sliding past another surface. So, friction. So let's just start off with a simple example here. Here is a some level surface, the floor, made of some material, and then there's, of course, a block sitting on this thing. Okay, with a mass m. So there are just a few factors that determine frictional forces between two surfaces. One of the factors is what the surfaces are made of, all right? So like steel on ice is going to have a lower coefficient of friction, is what they call it, than, say, rubber on dry concrete, right? So there's this number, it's a constant. It's called mu. Okay, that's the Greek letter mu, like this. Mu. All right, it looks kind of like an M. It's a Greek letter. It's the Greek letter mu. And it stands for a lot of things, but for our purposes right now, it is called the coefficient of friction. I'm sure I misspelled something here. Coefficient, two F's, who knows? Coefficient of friction, mu, okay? Which, of course, is related to the justified ancients of mu. Furthermore, known as the jams. You should look it up. Justified ancients of mu. Okay, anyway, everybody knows about Atlantis, but who knows about the lost continent of mu? Anyway, all right, so friction is kind of an interesting force, all right, because sometimes it's there and sometimes it's not there, all right? For example, suppose that there's this big block right here or whatever. You really can't tell how big it is until I draw something next to it, like a person. Wait a second here. Okay, I bet you didn't even think the block was going to be this big, did you? All right. So now you've got this person standing here, and they start to exert a force against this block. And the block doesn't move. All right, why doesn't the block move? Well, he's not pushing it hard enough. There's a frictional force between the block and the surface, and that frictional force wants to stop the block from slipping. So as soon as he exerts a force to the right, friction between the floor and the block starts up. We're going to represent friction with a lowercase f, okay? And just to make things more interesting, there are two kinds of friction. There's static friction, Static friction occurs between two surfaces when there is no slipping, like this situation right here. And there is kinetic friction. Kinetic friction is the kind of friction that happens between two surfaces when they are slipping or sliding past each other. And so these two both have their own coefficient, okay? They'll be close to each other, but typically the coefficient of static friction is going to be a little bit bigger than the coefficient of kinetic friction. That just means it takes a little more force to start something moving than it does to keep it moving, okay? And then, so the way that we represent those coefficients, like I said, is with mu. So there is a mu sub s for static and a mu sub k for kinetic friction. Sometimes we won't use the subscripts. You can tell from the problem whether it's slipping or not slipping, okay? So yeah, so this person here is going to, you know, and if he pushes this thing a little bit harder, increases that force some, friction is going to increase too. Friction is sometimes called a smart force because it seems to know what you're doing. Okay. Now, the thing is, though, this is static friction because the block is not slipping. But that frictional force can only be so large, right? And so eventually, you're going to exert a force here that is going to be greater than friction. And then the block will start to slide or slip or accelerate, okay? So let's say that you push this thing hard enough and you start it moving with a constant speed. All right, so let me redraw this. Where are you going, Larry? I think he's had enough physics for today. Oh, come on, I can do better than that. That's a little better. All right, so now, so this thing has a mass, m, and now it is going to be slipping in this direction with constant speed. Okay, it is now slipping across this surface, okay, because you're pushing it. Okay, and so we want to know, well, how much force is required to get this thing moving, for example, at a constant speed. And that's going to depend, again, on a couple of factors. Here is how you calculate how large this frictional force is. Friction. Friction, if it is slipping, then that means that this is kinetic friction, and that is equal to mu kinetic times n. N, as in n is the normal force acting on this thing, okay? And this coefficient of friction, it depends on what the surfaces are. It depends on what this block is made of, and it depends on what the floor is made of. All pairs of materials have the coefficient of friction, okay? And if you're going to be a civil engineer and design roads, or mechanical engineer and design machines with slipping parts, you need to know a lot about friction. So let's just put some numbers here with this problem, okay? Let me make some room up here too. Okay, so how about let's say that there's a coefficient of kinetic friction between these two guys, mu sub k equal to 0.5. This is a dimensionless number. Typically, it's going to be between 0 and 1. 0 being frictionless and 1 being pretty frictiony, okay? Like rubber on concrete, for example. And n is the normal force, all right? The more force there is pushing between these two surfaces, the greater that frictional force can be, okay? So, in the winter time, all right, it's a good idea to have a couple of bags of really heavy stuff in your back trunk for two reasons. If you get stuck, you can put like cat litter or whatever under your wheels, or it also makes your car heavier. That increases the normal force and increases friction between your tires and the road. All right, so let's say that this block has a mass of 100 kilograms. Actually, that's heavy. Okay. So, free body diagram, all right? Man, Listen to Robbie go over there. Let me redraw this. All right. So the forces acting on the block are its weight, mg. So in this case, if m is 100 and g is 10 meters per second squared, that is 1,000 newtons. And since the block is not accelerating up or down, the force that the floor exerts up on the block, that's the normal force, is also 1,000 newtons. And so that the frictional force acting to try to keep this thing from slipping is equal to mu times n. So in this case, that frictional force is equal to 0.5 times 1,000 newtons. So that frictional force is 500 newtons. So then how much force do you need to apply to get this thing to move with constant speed? It's exactly 1,000, it's 500 newtons, right? If it's moving with constant speed, that means that the acceleration is 0. Again, because we said that once you get it moving, it's going to move with constant speed. Now, to get it to accelerate initially, yeah, that's going to take, that force you're exerting against it's got to be a little bit greater than the frictional force. But once it's sliding with constant speed, the force you exert just needs to be equal to the frictional force, and it's going to cruise along with constant speed, right? So then the force you're applying here again is 500 newtons. And that's again because the net force acting on this thing is 0. Yes, if it's moving with constant speed, the net force on it is 0. All right? So let's do another problem then, okay? Okay. So I'm going to kick a block across the floor. And give it an initial velocity of 5 meters per second. Okay? And let's say that there's a coefficient of friction between the block and the floor, and that coefficient of friction is mu. Okay? We'll put a number on it if you want. 0.5, why not? Okay. And so then the question is, once you kick it, you stop kicking it. So it's going to slide a little ways across the floor and then stop. So then the question might be, how far will it slide until it stops? Okay. So this is a kinematics problem. We've done a bunch of these before. The only thing a little bit different now is we're also involving Newton's second law with this as well. Okay, so free body diagram. So when the block is sliding across the floor, what are the forces acting on the block? Okay, so well, the weight of the block is downward. That's mg. And there's a normal force, that's the force of the floor upward. That's equal to mg. And there's a frictional force acting to the left, causing the block to slow down. Once it leaves your foot or leaves your hands, there's nothing pushing it forward. There's friction acting on it towards the left, causing it to slow down. All right. And so in order to figure out how far it slides, we need to know the acceleration of the block. And to figure that out, we need Newton's second law. All right? So first we're going to find acceleration with Newton's second law. So net force equals ma. If this direction is positive, then the net force acting on this thing is minus F. All right. But we just said friction is equal to mu times N. So minus equals ma. Okay, but N is equal to mg. Let me get this stuff out of the way here. It's getting a little crowded. So minus mu mg equals ma. And now the m cancels from both sides. So yeah, you don't need another mass of the block. So the acceleration of this block is minus 0.5 times an n was... Oh, we don't know what n is. Well, sorry. 0.5 times g, which is 10 meters per second squared. Yeah, so that thing has an acceleration of minus 5 meters per second squared. Now that I know this acceleration, I can figure out what delta x is. Because I remember that, how about V final squared is V naught squared plus 2a delta x. V final is 0. So it's minus V naught squared divided by 2 times a is delta x. And so now you can plug in the numbers. Okay. So this is going to be minus 5 meters per second squared divided by 2 times minus 5. Okay. So the minus signs cancel each other out. And so then we have 25 upstairs divided by 10. So that gives us 2.5 meters for delta x. Okay. So there you go. Slipping and sliding.